Good afternoon, ladies and gentlemen. Welcome to another episode of Dave Does Math from Home. Today I have a very exciting episode for you. I'm pretty pumped about it. This is one of my favorite sections in all calculus. Today we talk about implicit differentiation, and hopefully in the process of talking about implicit differentiation we come to an understanding of why Leibniz's notation makes more sense than Newton's and why the chain rule is important. That's what's on the agenda. Before we get too far into this, we need to talk first and foremost about what implicit means in this context in terms of implicit differentiation. And in this context, implicit is a kind of function. The functions that we're used to look like this. Y equals something. A bunch of stuff is happening to the x variable, and after all of that stuff has happened to the x variable, all of that is set equal to y. This is explicit because it is y is isolated. Y doesn't have to be isolated for us to have a function or an equation or a graph. Here's a pretty famous example. X squared plus y squared equals 9. Not technically a function because the graph of this set of points doesn't pass the vertical line test. If you try to isolate this for y, you'll get y equals plus or minus the square root of something. So it's not technically a function, but it is implicit because it's not solved for y. And we can look at other implicit things that are functions, like the sine of y equals 3x squared. Here you go. Here's an implicit function. Y is not isolated, or we could make this even more interesting if we wanted to. Plus y. Ugh. There we go. Y is not isolated. There are two of them. They're on either side of the equation. Isolating y in this instance is going to be almost impossible because you'd have to find a way to undo the sign on this without affecting this. This is an implicit function now, which is still an equation with x's and y's in it that gives you one y value for each x you put in, but it's just not solved for y. That's what it means to be implicit. So implicit differentiation is the section where we learn how to take derivatives of things that look like this. We already know how to take derivatives of things that look like this. This is easy. Y prime here is 6x minus 12. Bam, done, finished. So today we're looking at how to take derivatives of things that look like this, or this maybe. We can take a derivative of this. It's not as hard as it seems. And to do that, we're going to talk a lot about Leibniz's notation and the chain rule and what those things mean for us. So we'll come back to these examples. For now, I'm going to erase it. It's worth noting that this derivative I wrote here, the y prime, this is Newton's notation. Quick history on calculus. Calculus was invented independently by two different people about 10 years apart. Newton did it first, and he's most often credited with it, but Newton was first and foremost a physicist. He invented calculus so that he could use it to do physics, and his notation reflects that. It's a very simple sort of notation for derivatives that he could use to find speed and acceleration given distance graphs and things like that. Completely independently from him, about 10 years later, a guy named Leibniz also invented calculus. And that's important for us because Leibniz was a mathematician. He wasn't doing this so that he could do physics. He was doing this so that he could do more math. And his notation when you understand the math of what's going on here, makes a lot more sense. So that's what we're going to talk about. And the first thing we're going to do is pretend that D means derivative of. We're going to pretend that that's what D means. So now if you take something like y equals x cubed as a function, if I ask for the derivative of y, the first thing we need to note is that I want dy. This literally means derivative of y. If that's what d means, d is derivative of, then this is the derivative of y. This is what I'm asking for. We know how to take the derivative of x cubed. That would be 3x squared. Seems easy enough. But wait, there's more. What if, secretly, unbeknownst to us, x was actually the sine of z? If x is also a function, then it has its own derivative. If this were true, then we would have the situation that y is not actually x cubed. Y is the sine of z cubed, and now the derivative of y would be 3 sine of z squared times the derivative of the inside. Because of the chain rule, that's really the situation that we're sort of trying to contrive here. What if there's weird chain rule stuff that we don't know about? So if x is a function, then we have to multiply by the derivative of that function as well. This derivative would be cosine. The cosine of z, sorry. So for the most part, we can see that these are almost exactly the same. Both of these things still have that the derivative of y is 3x, x is sine of z, so both of these things are 3x squared. That hasn't changed. 3x squared, this is just 3x squared. What's changed is, because x is a function, we have multiplied by this piece here, which is the derivative of x. So that's what we've added to this. This derivative of x piece got included because of the chain rule. And that was what happens if x is some function sine of z. Here's where I'm going with this. Anytime you take the derivative of something y equals something of x's, you don't know that x isn't a function. X could be a function. It's not clear that it is or not. Sometimes it's just an independent variable and you don't have to deal with it. Sometimes it's a function. That's never explicitly clear. Maybe it's a function. Could be. So, to sort of cover for that situation, if x is a function, we have to multiply by the derivative of that function because of the chain rule. If we don't know what function it is, we're just going to multiply by dx because of the chain rule. If x isn't a function, if x is just x, then the derivative of x is 1. And we're multiplying by 1, and we're not changing anything. But if x is a function, then we need to include this piece just to be safe. That's why we're putting a dx here. The dx comes from the chain rule, in case x is a function. The next problem then is we don't really want it to be there. If we're given y equals x cubed, then we want the derivative to be 3x squared. If x is a function, maybe it is, we have to put this there just in case. The thing is, I don't care if it is or not. I kind of just want to get rid of it. So we're going to divide both sides by dx. just to kind of push it to the other side of the equation so that we don't have to deal with it anymore. It cancels from here. Now you have dy dx equals 3x squared, which is the standard derivative that you all know and love. And this dy over dx is Leibniz's notation for the derivative. Newton would write y prime. Leibniz is going to write dy dx because this means the derivative of y divided by any potential maybe derivatives of x that might show up because of the chain rule. This is a safeguard against weird chain rule nonsense. And again, if x isn't a function, then we're just dividing by 1 and nothing changes. But in case x is a function, we put this here, and that has become the notation for Leibniz. So this technique, where we pretend that d means derivative of, and we take the derivative of an entire equation piece by piece, and whenever we take a derivative of these x pieces, we add a dx on the back end. This is how implicit differentiation is going to work. When we do this implicit differentiation stuff, we don't know for certain which variable is dependent and which variable is independent. When we have stuff like this, this is an explicit function. It's very clear. Y is dependent because it's isolated. X is independent because stuff is happening to it. Like, this relationship is clear. When it's implicit, we don't have that clearness of the relationship. If you have something like y squared plus x squared equals 9, maybe x is the variable you're plugging stuff in for, and then you're finding y. Maybe it's backwards. Maybe you're plugging stuff in for y and finding x. So we're not sure which one is a function of the other. Could be a function of both, which is why we use dy's and dx's on both of them according to the chain rule. So I feel like I've talked around this idea enough. I think it's time to do some examples. Hopefully the examples make all of the stuff I was saying more clear. While I'm erasing, I also want to mention this technique for doing the chain rule is one of the first big departures that I'm making from the book. If you look up implicit differentiation in the book, it'll tell you a moderately different technique from the one that I'm about to show you. So we can talk about that technique in a little bit and how it's the same and slightly different from the one I'm showing you. I just want to warn you that they are different. So let's go back to our circle. X squared plus y squared equals 9. If I want the derivative of this, that means that I want dy over dx. This is the goal. And I'm going to get these dy's and dx's by taking the derivative of this entire thing piece by piece. The derivative of x squared is 2x, unless x is a function. If x is some function, I would have to multiply by the derivative of that. So because of the chain rule, this is going to be 2x dx. The derivative of y is 2y dy. And the derivative of 9 is 0. So x squared turns into 2x. That should be pretty familiar. Y squared turns into 2y. That should be pretty familiar. We're attaching a dx here and a dy here because of the chain rule. At least one of these is a function of something else. So when we take the derivative of this inside-outside function, use the chain rule to multiply by the derivative of the inside. That's where these dx's and dy's come from. That means derivative of x, derivative of y. And now, once you've done this derivative step, all we have to do is algebraic manipulation to move things around and get these dy's and dx's to look like this. So I'm going to start by subtracting this from both sides. Here's a quick word of advice when you're doing this algebraic manipulation. dx and dy are always their entire own unit. This isn't d times x. This isn't multiplication. This is one object and its name is dx. So like some students, when they see this, they want to try and like compress this. Like they want to multiply these two x's together to get x squared and leave the d by itself. You can't do that. Dx is its own object. So I'm subtracting 2x dx from both sides. I get 2y dy. I need to learn how to draw a y. 2y dy equals negative 2x dx. Now I have this dy. I need a dx on the bottom, so I'm going to divide by dx. I'm going to cancel these guys out. I have the dy dx that I want. It's being multiplied by 2y. So I'm also going to divide by 2y. Cancels out here. I have now dy dx equals, these 2's will cancel, negative x over 1. And this is the derivative. If you plug in any combination of x and y values that are on this circle, you can find the slope of the line tangent to the circle at those coordinates. So, this is a bit of a practical example because we can visualize this. We know it's a circle. We can interpret this result. I'm going to see if I can remember the other weird... No, I'm not. This video is 17 minutes long. I'm going to end this video and we're going to start the next one with whatever weird nonsense I started this video with. I'm going to take an implicit derivative of that. Stay tuned.